Good morning, students. And today we are dealing with the subject of ME 8692, first unit, Introduction to Finite Element Analysis. In this unit, we are going to study about the historical background of the finite element analysis and field problems of mathematical modeling in engineering, then governing equations, initial eigenvalue problems, boundary value problems, then weighted residual methods, and Ritz technique, and also we are going to study about basic concepts of the finite element. Okay, by studying this first unit, we can able to apply the basics of the finite element equations in the problems. Okay, now we are going to study about an important topic, general steps of finite element analysis. So in this finite element analysis, there are main three steps are there. Okay, first one is pre-processing, analysis, and post-processing. Pre-processing, analysis, and post-processing. In pre-processing, there are two important steps are there. One is discretization, another one is numbering of nodes and elements. First, when we are taking the element, first we are going to discretize the element and giving some numbering of nodes and elements. We are going to give numbering to the nodes and elements. Then in analysis, here selection of displacement function, define the material behavior, derivation of element stiffness matrix and equations, assemble the element equations, apply the boundary conditions, solution of unknown displacements, computation of the element stresses and strains. First, in this analysis, we are going to select the displacement function. To solve or analyze the particular element or an object, first we are going to select the displacement function. Then we can able to define the behavior of the material. Then derivation of element stiffness matrix and equations. We should derive the element stiffness matrix and equations. With the help of this element stiffness matrix, we can able to find out the equations and also a particular solution. Then after finding the equations, we should assemble the element equations. We found out the element equations and assemble it on the particular element. Then we should apply the boundary conditions. After the application of the boundary conditions, we can able to find out the solution for the unknown displacements, and we should get the stresses and strains of the particular element. And the final one, post-processing. After the analysis, we should interpret the results or show or read the results from the output. This is the chart for the general steps of finite element analysis. Now, this is the first one that we studied in the discretization in the pre-processing. In the pre-processing, this is the first step, discretization of the structure. This discretization of the structure is nothing but it is a art of subdividing a structure into a convenient number of smaller elements is known as discretization. When we take an element, consider this a bar element, we can able to split this bar element into a convenient number of smaller elements to find out the solution for the particular element. These smaller elements are classified as one-dimensional elements, two-dimensional elements, three-dimensional elements, and also axisymmetric elements. These are the classification of the smaller elements. Okay, in one-dimensional elements, a bar element and beam elements are considered as one-dimensional element. Bar element and beam elements are considered as a one-dimensional element. The simplest line element is also known as a linear element, and it has two nodes, one at each end. As shown in the figure, one end is on the left side, one node is on the left side, and the other node is on the right side of the bar element. Then the second one is two-dimensional elements. Two-dimensional elements. In the previous diagram, we saw the one-dimensional element. Now we are going to see two-dimensional elements. The triangular element and rectangular elements are considered as the two-dimensional elements. But we considered bar element and beam elements are considered as one-dimensional element. Here we are considering two-dimensional element as triangular element and rectangular element. These elements are loaded by forces in their own plane. The simplest two-dimensional elements are below. We can see that triangular element and also rectangular element. When we consider this triangular element, there are three corners are there. So for this triangular element, we can able to get the three nodes. For rectangular element, there are four corners are there. So we can able to get the four nodes for the one element. And now we are going to see the three-dimensional elements. In three-dimensional elements, and most commonly, tetrahedral and hexahedral elements are considered as three-dimensional elements. These elements are used for three-dimensional stress analysis problems. Three-dimensional stress analysis problems, we are using these elements like a tetrahedral element and hexahedral element. These elements are used for three-dimensional stress analysis problems. Normally, we are using these tetrahedral and hexahedral for stress analysis problems. So we saw the figure as a tetrahedral element and also hexahedral element. Normally, tetrahedral element is similar to the triangular element, but in triangular element we can able to get only three nodes, but here in tetrahedral element we can able to get four nodes. In hexahedral element we can able to get 8 nodes, but in rectangular element it is similar to the rectangular element, but in rectangular element we can able to get 4 nodes. Here in hexahedral we can able to get 8 nodes. And the last one is axisymmetric element. In this axisymmetric element, it is developed by rotating a triangle or quadrilateral about a fixed axis located in the plane element through 360 degree. Okay, in this axisymmetric element, it is nothing but we are fixing a plane. Okay, it is a xy plane or xyz plane. We are fixing a plane. When we rotating a triangular element, from the initial point to 360 degree rotation of about the axis, about the fixed axis, we can able to get one symmetric shape equally about to 360 degree. So that shape is called as axisymmetric element. When the geometry and loading of the problems are axisymmetric, these elements are used. Okay, so this is the axisymmetric element. It is nothing but we are going to fix an axis about to xy plane or xyz plane. When we rotating a triangular element from the initial point to 360 degree of rotation and to the same point, we get an axis is a symmetric plane about the fixed axis. That is called as axisymmetric element. Now the second one in the first part, preprocessor, numbering of nodes and elements. Numbering of nodes and elements. In this numbering of nodes and elements, it should be numbered after discretization process. The numbering process is most important since it decides the size of the stiffness matrix and it leads a reduction of memory requirement. While numbering the nodes, the following condition should be satisfied. Okay, when we take an element, we can able to split the element as we need it. Split the element, it is simply called as a discretization. For our convenience, we can able to split the element into different convenient number of smaller elements. Okay, while we splitting the elements, we are going to give a numbering for each element and also for each nodes. Normally, for each element, we have two nodes. For that two nodes, we are giving number. So if there is a 5 elements, we have 10 nodes are there. For each element, 2 nodes. But while it is joining, for the first element, the node numbers are 1 and 2. For the second element, the node numbers are 2 and 3. For the third element, the node numbers are 3 and 4. And for the fourth element, the node numbers are 4 and 5. And for the fifth element, the node numbers are 5 and 6. Okay, while we giving this number, that's a formula to satisfy the condition. Maximum node number minus minimum node number is equal to minimum. So if the maximum node number is and minimum node number is reduced from the maximum node number, we can able to get the minimum value. So we can able to see this longer side numbering process. Here there are totally 15 number of elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and 15. There are 15 number of elements. Here for this line we have 2 nodes. So if it is a rectangular element, we have 4 nodes. 4 nodes. Okay. So we considered this as a rectangular element. So for the first element we have 4 nodes, 1, 2, 7, 8. For the 8th element we have 4 nodes, 9, 10, 15, 16. So in this process, now we are considering only one element, that which is a third element. Third element, we are considering the third element. Here 3, 4, 9, 10 is the node number. So this is third, we are considering third element. The node numbers are 3, 4, 9 and 10. Okay, here the maximum node number is 10. Maximum node number is 10. So minimum node number is 3. Now we should be able to get the difference between the maximum node number and the minimum node number. So what's the difference? This is the condition. Maximum node number minus minimum node number. So difference is 7. So difference is 7. This is the longer side numbering process. So now we are going to see the shorter side numbering process. Shorter side numbering process. Longer side is nothing but the node which is starting from the one point and it moves in a horizontal way. But shorter side is nothing but it moves in a vertical way. So here the same 15 number of elements are there. So the nodes are going from vertical way 1, 2, 3, 4 and 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 10, 20 and 21, 22, 23 and 24. Here also we are considering third element. So here the node numbers are for the third element 9, 13, 10, 14. 9, 13, 10, 14. So for the third element. So here the maximum node number is 14. Minimum node number is 9. What's the difference here? The difference is nothing but 5. So we are we came to know that the shorter side numbering process followed in the finite element analysis, it reduced the memory requirements. Why we are selecting this shorter side numbering process? Because here the difference is 7, here the difference is 5. So what is the condition? Maximum number minus minimum number, that we should get the value of a minimum. So here the minimum process is shorter side numbering process. So we are following this number pattern. Okay, for this is the second step. Now we are going into the analysis. Here in analysis, we are going to selecting the displacement function or interpolation function. We are going to selecting the displacement function or interpolation function. Here we are going to choose a displacement function for each element. Here the polynomial of linear, quadratic and cubic forms are frequently used as displacement functions because they are simple to work within finite element formulation. Mostly used polynomial type of interpolation functions are, it is easy to formulate and compute with the finite element equations, and it is easy to perform differentiation or integration, and accuracy of results can be improved by increasing the order of polynomial. So these are the three main conditions for using the type of interpolation functions in polynomial type of interpolation functions. So these are the linear polynomial and quadratic polynomial. In linear polynomial, one-dimensional problems, pi of x is equal to a0 plus a1x. In two-dimensional problems, pi of x comma y is equal to a0 plus a1x plus a2y. In three-dimensional problems, pi of xy is equal to a0 plus a1x plus a2y plus a3z. In the same way, in quadratic polynomial problems, for one-dimensional problem, pi of x is equal to a0 plus a1x plus a2x squared. For two-dimensional problems, pi of x comma y is equal to a0 plus a1x plus a2y plus a3x squared plus a4y squared plus a5xy. And for three-dimensional xyz problems, a0 plus a1x plus a2y plus a3z plus a4x squared plus a5y squared plus a6z squared plus a7xy plus a8yz plus a9z. So this is the condition for the linear polynomial and quadratic polynomial. Now we are going to see the fourth step. Define the material behavior by using strain displacement and stress strain relationships. By using the strain displacement and stress strain relationships, we are going to define the material behavior. So here, for strain displacement and stress strain relationships are necessary for deriving the equations for each finite element. Here in stress strain relationship, it is given by strain E is equal to du by dx. Here u is nothing but displacement field variable along x direction, and E is nothing but strain. The stress strain relationship is given by sigma is equal to capital E into small e. So sigma is equal to stress in x direction, E is equal to modulus of velocity or Young's modulus. So this is the stress strain relationship for defining the material behavior. Now, derivation of element stiffness matrix and equation. Derivation of element stiffness matrix and equation. Here, the general finite element equation is nothing but F is equal to K into U. Here, the force, load, which is moved from the first F1, F2, F3 up to Fn. Likewise, the stiffness matrix also move from K11, K12, K13 up to K1n. Likewise, K21, K22, K23 up to K2n, and up to Kn1, N1, Kn2, Kn3 up to Kn for the stiffness matrix. And for the displacement function, U1, U2, U3 up to Un. This is the derivation of element stiffness matrix and equations. In equation is nothing but F is equal to K into U matrix. Now, for the next step, assemble the element equations to obtain global or total equations. How we are going to assemble these equations? The element equation that we got or obtained in the previous step, we are going to add it together by the equation of each element, and finally it is assembled in the formula of the general finite element equation. F vector is equal to K matrix into displacement matrix U vector. So F is nothing but global force vector, K is nothing but global stiffness matrix, and U is nothing but global displacement vector. Now, in the next step, we are going to applying the boundary conditions. We are going to apply the boundary conditions in the previous step. It is nothing but the global stiffness matrix is a singular matrix. K is nothing but it is a singular matrix. The determination of the stiffness matrix is equal to 0. So, in order to remove this singularity problem, the boundary conditions are applied so that the structure remains in place instead of moving as a rigid body. So, the global equation to be modified for the boundary conditions of this problem. Okay, so after the application of these boundary conditions that we applied of these boundary conditions, the next is the solution that we have to get for the unknown displacements. We need to get the solution of the unknown displacements. So in the step 6 that we saw that F is equal to K into U. So in this step, we are going to apply the boundary conditions, and then we are going to solve that equation, and we can able to get the unknown displacements. And the last step in the analysis, we can able to get the stress and strain matrices, the stress and strain values by using the elements by using these nodal displacements. And in this step 9, the element stresses and strains we can able to get from the unknown displacements or nodal displacements. So in the previous step, we found out the unknown displacements, and now we call it as a nodal displacements. So by using the nodal displacements, we can able to get the strain value on and also the stress value. So how we are going to get the strain value? Strain E is equal to du by dx. So du by dx is nothing but u2 minus u1 divided by x2 minus x1. This is the strain value for the first element. So if you want to find out the strain value for the second element, the formula will change as E2 is equal to u3 minus u2 divided by x3 minus x2. So this is the value. Here u1 u2 are the displacements that we get from the node 1 and 2, and actual length of the element x2 and x2 minus x1 is nothing but actual length of the element. Likewise, we are going to calculate the stress value. So stress is nothing but sigma is equal to capital E into small e. Capital E is nothing but it is a Young's modulus, and E is nothing but it is a strain. So the final step, interpret the results. It is nothing but the post-processing. After the solution that we get from the analysis, we are going to show the post-processing results. It is nothing but analysis and evaluation of the solutions result. It is referred to as a post-processing. So in the post-processing, the post-processor computer program helps the user to interpret the results by displaying them in a graphical form. So the user may get the results of the particular solution with the help of the computer programs. It shows the output results in a graphical form. So this is the general steps of finite element analysis that we studied in the three different categories: pre-processing, analysis, and post-processing. So we get a clear view of these general steps of finite element analysis of the three terms: pre-processing, analysis, and post-processing. Thank you.